Monitoring the movements of people and in general their activities is fundamental for many human-centered IT applications, which potentially impact on society through security and surveillance, ambient assisted living, sports analysis and interactive entertainment. Thanks to their unobtrusive nature, camera-based systems are of particular interest in these fields. Moreover, video streams encode large amounts of information from the scene, potentially supporting a highly detailed analysis. However, extracting relevant content from such images in unconstrained settings is challenging and requires substantial progress beyond current state of the art.
From a scientific point of view, some of the major challenges here are real-time handling of large and persistent occlusions among the moving targets, consistent propagation of uncertainty and ambiguity, often present in the estimates in form of occlusion and clutter, adaptation to changes in the environment, such as varying lighting conditions and background motion, and the online detection of a newly entered target and their visual modeling. The research carried out here at the Technologies of Vision group Fondazione Bruno Kessler has addressed these four issues, and the results have been used to implement a multi-camera, multi-people tracker, the so-called Smartrack system.
To detect the presence of a new target in a predefined enrollment area, a coarse three-dimensional shape model resembling a standing person is projected into each of these images using a calibrated camera model, which is then matched against observed edge features. If the match is above a threshold, then a color model of the new target is extracted from the projection area and a new track is initialized. To update spatial position over time, a number of new hypotheses are generated around the previous estimate and their likelihoods computed by matching the target's model against the color histograms extracted from inside the projected shape. In a final resampling step, the hypotheses with low match scores are rejected, whilst the others are maintained. The resulting particle filter can follow agile motion and is less prone to get distracted by background motion. The number of position hypotheses that are generated during the propagation step is updated on the fly according to the amount of estimation uncertainty, measured in terms of output entropy. The filter can therefore adapt to critical situations by maintaining the uncertainty present in the data. By refining the target shape model and extending the estimation space, additional information can be extracted using the same tracking framework. For example, people's head orientation or more detailed information about body pose and posture. To account for occlusions amongst multiple targets, a joint extension of the color likelihood has been adopted. It explicitly reasons about occlusions in terms of consistent shape projections and visibility information. It can even handle complete occlusions from a single view by bounding hypotheses of a target to the occlusion volumes generated by the other bodies if it is not observed elsewhere. In general, methods that implement such models do not scale, as they lead to algorithms whose computational complexity grows exponentially with target number, ruling out their utilization for real-time applications. By adopting an approximate filter model dubbed hybrid joint separable, the single target marginals of the joint multi-target distribution can be computed with a complexity that has a quadratic upper bound, thus solving the curse of dimensionality for the occlusion problem. This enables the system to track up to 12 occluding targets in real time using current hardware. Recently, the tracker has been extended to include online detection and the model acquisition of new targets as an integrated task. Motion edges unexplainable by tracked objects are used to generate position hypotheses for new targets in locations where the outline of the projected shape model matches extracted edges. This method can be formally embedded into the adopted Bayesian framework, providing a detection prior that has been derived as the inverse of an inclusion-robust contour likelihood. With this extension, the system can monitor the behavior of people in complex and non-collaborative environments, making it a transparent and non-invasive technology, ready to support applications in fields such as security and surveillance, domotics, sports analysis, and interactive entertainment.